This lecture will introduce how to generate pulse width modulated signals using a PIC microcontroller and how they can be used to control DC motors. DC motors are easily controlled by a PIC microcontroller but often require external hardware. In this lecture we will discuss how a digital signal from a microcontroller can be used to generate the control signal necessary to control external transistor-based circuits that can allow us to vary the speed on a DC motor. A transistor-based circuit, such as the one seen here, allows the load, which would be the motor in this case, to turn on and off at a set interval, a pulse width modulated signal. The PWM signal would come in here as VG. This is a field effect transistor, and effectively what's happening here is as the voltage on the gate rises above a certain threshold, this transistor now behaves like a short circuit, allowing current to flow through from VSS to ground. When VG falls below a certain threshold, this transistor effectively behaves like an open circuit, meaning that there is no current flowing through the load. What happens here, we also need this flyback diode, because if you remember, a motor is primarily an inductive load, and inductors do not like to instantaneously change their current. So if this current coming through here, the ID, which will be the drain current, so a transistor like this has a gate, a drain, and a source. And so the ID is the drain current, meaning the current going this direction from high to low toward ground. If that were to change instantaneously, that could cause severe damage to the motor. And so instead of all of the current going immediately from some positive current directly to zero instantaneously, this flyback diode allows a pathway for that excess current to escape while we are slowing down to the zero current condition. And so in this case we're talking about an on-off signal where when VG is above a certain threshold, nominally a VDD signal or a 5-volt signal, then the motor will be on, and when it is below that threshold it will be off. And we will use a pulse width modulation signal to determine how much time is spent on and how much time is spent off. We will generate square wave signals using our PIC microcontroller in order to do that. And to vary the speed, we will vary the duty cycle. And hopefully you remember from a previous Introduction to Engineering course that the duty cycle is the ratio of the time that that signal is high to the overall period of the signal expressed as a percentage. So the maximum motor speed is going to occur when we have 100% duty cycle. That would mean that we are always high and never low. The minimum would be at 0% duty cycle, meaning that you are always off and never high. And a half speed signal would be at 50% duty cycle, and that would mean that the amount of time high in the square wave was the same as the amount of time low. So here you see some example PWM signals. A duty cycle of 10% would provide a fairly low speed motor movement, and so this would mean that the signal would be on 10% of the time and off for 90% of the time. Effectively what that means is the motor is not turning on and then going to a stop. It's not going to a stop when it's down here. It's just slowing down, and you see an averaging of how quickly it would go. The way I like to think about it is the time that this is high is effectively like giving it a push. And so if you think about giving someone a push while they're on a swing set, for example, they can continue moving even though they're not being pushed, but how often you push them determines how quickly they can go on that swing. And so as you get into 30%, 50% duty cycle, you're pushing more often. You can also think about this like a person riding a skateboard. So if you are pushing off on the ground and then you glide on the skateboard, you can keep going for quite some time. But the faster you push off on the ground, the more often you push off on the ground, the faster you're going to be able to go on that skateboard. So this 90% would demonstrate a signal controlling a motor where you are pushing off a lot relative to the time that you are gliding. This would be a push and glide at an even ratio there, 50%, half the time pushing, half the time gliding, and so slower signals at lower duty cycle, faster motor speed at higher duty cycle. So how can we generate a pulse width modulated signal with the PIC? Well, we could brute force it, meaning that we're going to choose one of our output pins to be the output bit. We're going to turn on that bit. We're going to delay for however long we want that signal to be high, turn it off, and then delay again. Very similarly to what we did in the music lab. So in the music lab, we had 50% duty cycle, but now we are going to choose a different duty cycle depending upon how quickly we want this motor to go. And then we can just continually loop through, generating more periods of our pulse width modulated signal at our desired duty cycle. Well, that will work, but there are some problems with doing it that way. Every time you toggle on and off and just continue to do this in a loop, your processor cannot perform any other task. And so it does take processor resources, it does limit your opportunity to do something else. And so the nice thing about our PIC microcontroller is we have the ability to automate the generation of a pulse width modulated signal. And so what we will do is use the Timer 2 module. The Timer 2 module has built in two different modules for capture and compare. And so what we will capture, compare, and pulse width modulation. That's what the CCP stands for. There is CCP1, which is on pin RC2, the same pin there, and there's CCP2, which is on the same pin as RC1. So you can actually control two independent pulse width modulated signals if you wanted to control two motors. For our purposes in this class, we will be controlling only one motor, and we will be using the CCP1 module, which will produce an output on the RC2 pin. There are several different registers that we will need to configure in order to develop our PWM signal at the desired frequency and the desired period so that we can control our module. You will note that there are parallel registers here, and in fact in your data sheet there is oftentimes an X placed in the place of these numbers. So we will be configuring CCP1, and so we will have the CCPR1L. There is also a CCPR2L if you were to configure CCP2. There's also a CCP2CON that goes along with the CCP1CON register, and that is likewise to control the CCP2. But for the remainder of this lecture, we will focus on the registers required to control CCP1. But just keep in mind in your data sheet that you may see, instead of CCPR1L, you may see CCPRXL, because there are two different ones and those registers behave in the exact same way. PR2 is the same for both of those modules. We'll talk about that in just a moment. And T2CON is the same for both of those modules. That is the configuration for Timer 2. So let's dive into some of these registers and then have a general explanation of how we're going to configure those different registers to develop the pulse width modulated signal as desired. So the first register to be aware of is the PR2, and that is short for the Timer 2 module's period register. And what this will allow us to do is to configure the overall period of the PWM signal that is coming from the pulse width modulation output. And what will happen is Timer 2 is an 8-bit timer, much like Timer 1 that we've discussed previously, and it will increment starting at 0 until it reaches the value set in PR2. Now the default value there is FF hex, and so it would increment just like Timer 0 does, from 0 all the way through to FF and then overflow. You can actually choose when it overflows by replacing the value in PR2. But for our purposes, and I'll explain why later, we will use FF in PR2 for this lab. And so you can see here the equation for how long the period is. The period, as a matter of microseconds, is based on this formula here. The value in the PR2 register plus 1 times 4 times the period of the oscillator. So this is dependent upon the crystal oscillator that we have. And for hours, since we are using the 8 megahertz crystal oscillator, it will have a period of 0.125 microseconds. If you were to turn on the 4 times PLL, you would again divide that by another 4. And then there's also an opportunity in the timer 2 module to establish a prescale. So if you were to choose to do that, that would be just like we did in timer 0. You can prescale how long you want things to run so that it only increments every couple of periods, every 4 periods, things like that. And that would allow you to elongate the PWM period. We are not going to be using the prescale to change things as we go. There will be one set value that we are going to be using throughout, and we'll talk about that in just a little bit. The CCPR1L and part of the CCP1CON register are used to control the duty cycle of the PWM signal. And so the least significant bits are in bits 5 and bit 4 of the CCP1CON register, and the most significant 8 bits are in the CCPR1L register. Also, in the lower 4 bits of the CCP1CON register, we will set that to 1, 1, and then 2 don't cares. We'll just use zeros there. And that will put us into the PWM mode. So timer 2 can be used in a variety of modes. You can do capture, you can do compare, and you can do PWM. We will not discuss in this lecture the capture and compare module. You can read about that in the data sheet if you're interested. But we will just focus on PWM. And so in order to do that, we need to put 2 1s and then don't care, so we'll just put zeros in the place of those don't cares. If you look in the data sheet, you can find equations 29.2 and 29.3, and they showcase how the pulse width is calculated and how the duty cycle is calculated. And so we've already discussed the pulse width, and that is based upon the value that for the overall period, rather. But now this is how long we are going to actually be high during that period. And so that is based on your value in the CCPR. We're going to use 1 because we're doing CCP1, but notice this is what your data sheet does when it puts X in those places. So we're going to be determining our pulse width of how long we are high relative to the overall period. And so this colon here indicates that we're concatenating, meaning we're putting together. So CCPRXL is going to be an 8-bit register, and then we're putting together the other 2 bits here, meaning we have a net of a 10-bit value. And then we multiply that by TOSC, multiply that by the prescale. The duty cycle is computed, as you see here, as the ratio of that concatenated value divided by 4 times the PR2 plus 1. So let's see some examples to figure out what our duty cycle would be. If we let PR2 be FF, that's our default, and that's going to be 255 decimal, and then we choose to make CCPR1L a 1 in the most significant bit and zeros everywhere else, along with zeros in the CCP1CON bits that correlate to the least significant bits of our duty cycle, then what we have when we put all of those bits together is a value in binary that is worth 512 in decimal. Then if we take that 512 and divide it by 4 times PR2 plus 1, so this is our PR2 value of 255 plus 1, so that gives us 512 divided by 4 times 256 works out to 512 divided by 1024. If we express that ratio as a percentage, that gives us a 50% duty cycle. If we let PR2 be again FF, or 255 base 10, and then instead of setting the most significant bit in our CCPR1L, we set the next to the most significant bit, then what we have when we put things together is a decimal value of 256. Plugging that into the formula, that works out to a 25% duty cycle. So in general, if you let PR2 be the default value of FF, what that means is your most significant bit of CCPR1L is going to be worth 50% duty cycle, and each of the next bits, as you go on down from most significant to least significant, each of the next bits just divides by 2. So the second most significant bit is going to be worth 25%. The bit after that would be worth 12.5%. And then if you get all the way down to the 2 least significant bits, then we're talking about an order of magnitude of 0.2% and 0.1% respectively. And so that will be virtually insignificant unless we really want tight speed control on our motor. you're not going to notice to the naked eye a duty cycle difference of 0.2% or 0.1%. So if you do have an application where you do certainly want very tightly controlled speed of a motor, certainly you would want to set those bits. But we're going to simply make them 0, because for the purposes of what we're going to be doing in the lab, where you're going to be controlling a motor, you will not need to have that tight of control on the speed, and so we will just set those to 0. T2CON is another very important register. So bit 7 there is unimplemented. Bits 6 through 3 are the output post scaler, and we're just going to set all of those equal to 0 because we're just going to use a 1-to-1 post scaler. We do certainly need to turn on the timer 2 module in order to use it to do anything, but specifically we need it to do the pulse width modulation. So we need that turned on. And then our prescaler, we are going to use a prescaler of 16. So our least significant 2 bits we need as 1 and 0. In CCP1CON, we've already talked about the middle bits there, the 5 and the 4, which are the least significant bits of the duty cycle. We also should look at the other bits that are in there. So bits 7 and 6 are unimplemented. So sorry about the typo there. That should not be an E. Unimplemented. And so we will set that to 0, 0. And then our least significant 4 bits we will set to 1, 1, 0, 0 to put us in PWM mode. So let's just review what these registers are doing for us and understand a little bit more of what's happening underneath the hood when we get into the timer 2 module, the CCPR1L register, and the timer 2 register, and some comparators that are allowing this PWM signal to be generated. So what you'll notice over here, let's start on the right hand side. These are the CCP pins. So you have a CCP1 and a CCP2. So notice it has CCPX. And so the output from this circuit here will come onto those pins. You notice that we have a tri-state buffer here. So depending upon what you put for your tri-state, if you have a 0 there, then that will allow this signal to come on out. And so you must configure that pin as an output by putting a 0 in the corresponding TRIS-C register. And otherwise, you will, even though you're generating some signal internally, it will not reach the output pin. So it's important to configure the tri-state or the TRIS register for our output pin. And now if we get into what's happening in here with our CCPR1L and our timer 2 and our PR2, then you will see what happens. It uses an RS flip-flop in here. And so let's look at the first part. The CCPR1L and the least 2 significant bits are put together as a 10-bit register, and that gets copied into CCPR1H. And so that is really just a place where we copy things. You cannot read it. That's just used for this comparator purpose. And so a comparator is comparing the value that is currently in the TMR2, which is our counter there, counting time that has surpassed, and it's comparing it to the CCPR1L. And so once those are equal, then you have a 1 that gets put out here on the R of this RS latch. And so in this case, if you have a 1 there, that is going to generate the falling edge within the PWM signal. So it will go to a rising edge later. We'll talk about when that gets generated, but it will have risen. It will delay so long as the timer is counting until it reaches the same value as is in this 10-bit concatenation of CCPR1L and CCP1CON. Once it is, it will then reset it. Now down here, what you will notice is that timer 2 is being compared against the PR2 register. And so if you leave that at FF or you set it to some other value, what you are going to see is it is going to keep incrementing, and then once those values are equal, then it will do a few things. It will clear the timer back to 0, and then it will also hit the set, or the S, on this RS latch, and that will give us the rising edge of the PWM signal. And so you're going to, every time this resets, so let's say the timer is reset back to 0 because this comparator was equal, you're going to have a rising edge. So let's look at this. I will draw that. So right here, once this is starting out at 0, we're going to have a rising edge on our PWM, and we are going to keep incrementing our timer 2. It's going to go from 0 to 1 to 2 until it gets to the same value that we have set in the CCPR1L concatenated with the CCP1CON's middle bits. Then once that's equal, now our PWM signal is going to go low, and then it's going to stay low until our timer 2 keeps incrementing and equals the PR2 value. Then it's going to go back high again, and it's going to repeat this same process. And so it will generate this over and over and over again until you decide to change either the PR2 or the CCPR1L. And so we will put into our PR2 FF, so that will have the timer 2 reset in the same way that timer 1 does when it reaches FF and overflows back to 0, 0. That will allow us the longest period possible. And then we will choose our CCPR1L based upon our desired duty cycle. So if you wanted 50% duty cycle, then CCPR1L would be half of the PR2 value. The external hardware that we will be using is an H-bridge. And so an H-bridge is used to drive a motor forwards and backwards. In our case, we will simply be using it to drive the motor forward. And so what's important to understand is our motor here in the middle is taking from a positive voltage, so this would be connected to, in our case, plus 12 volts. So we are using a 12 volt DC motor, and this down here would be our ground signal. And what we are going to do is input a PWM signal on one of the inputs here. And so we can put in our PWM here. And that is going to allow us to have a closed path from the 12 volt signal as we close this path here, and then the current can go through the motor, and then we will have a closed path coming out here, and that allows us to go this way. You can also change the direction if you put in a PWM signal in here, and that would allow the current to instead flow this direction through the motor, and that would reverse the direction. So we can use PWM signals on either end to allow us to rotate clockwise or counterclockwise. In our lab, we will just use a single-ended PWM, so it will just go in one direction. But if you have a full H-bridge, you would be able to drive both forward and backwards. We are going to be using the SN754410 half H driver. And what that will do is take in digital logic inputs and amplify it to the voltages necessary to control the motor. And so our PIC can only output up to 5 volts. That will be the 5 volt PWM signal, but we need a 12 volt PWM to control our 12 volt DC motor. And so we will input for VCC1 a 5 volt logic high. You can get that from your VDD off of your board, and then to control the motor we will be using a 12 volt supply. And so I would like for those who are able to come to the lab. We will set up times for you to do this, so everything will be socially distant, and you will be able to connect to the 12 volt power supply and be able to test out your software and your hardware setup. So on this particular chip, I will talk more about this when we get into the lab, but you will have multiple sides on there, and so you can independently enable one side and the other. And so we will connect the PWM to a 1 amp source that will have 12 volts, and we will have our motor output on the 1Y and the 2Y. And the data sheet will be posted on Canvas. I will go over that more once we get into the lab exercise and once we talk about the in-class exercise.